In this video, we apply the Jacobi method and the Gauss Seidel method with the help of the software Mathematica to generate sequences of approximations for the solution of a system of linear equations. For this exercise, we illustrated two numerical methods using this system of equations. Observe that the system of equations is strictly diagonally dominant, so that the sequence of approximations that each method generates is guaranteed to converge to the exact solution. We solve for x1 in the first equation, so that x1 equals 1.8 minus 0.4x2 plus 0.2x3 minus 0.2x4. We solve for x2 in the second equation, x3 in the third equation, and x4 in the fourth equation. We start with the Jacobi method on Mathematica. First, we choose the initial estimate, or the seed for the sequence of approximate solutions. Let's set x1 equal to 1.8, x2 equal to 0, x3 equal to 2, and x4 equal to minus 0.5. We wish to point out that it is generally a good idea to include decimal points for the initial values so that the calculations are carried out using floating point numbers. This helps avoid computation overflow errors. Simply put, we don't want our machine to crash. For the iterations, we use a do loop. We have a set of commands within the do loop, so we use the curly brackets. The first command is calculating the new x1. x1 equals 1.8 minus 0.4x2 plus 0.2x3 minus 0.2x4. From equation 2, x2 equals minus 0.25x1 plus 0.25x3 minus 0.25x4. Now we have a slight problem, in that x1 had just been replaced with whatever value we get here. This means that in calculating x2, x1 will be replaced by the new value of x1, which is not how the Jacobi method works. So instead of using the variable x1 on the left side for the first command, we use the temporary variable a to store the new x1. This way, the old value of x1 does not get thrown out. We do the same thing for x2, so that for the second equation, we have the temporary variable b equals minus 0.25x1 plus 0.25x3 minus 0.25x4. For x3, we have the temporary variable c equals 2 minus 0.25x1 minus 0.25x2 minus 0.25x4. And for x4, this time we have the temporary variable d equals minus 0.5 minus 0.25x1 minus 0.25x2 plus 0.25x3. We'll print the new values of x1, x2, x3, and x4. For tracking purposes, we will also print on screen the iteration number I. The variable I will be the counter within the do loop. Along with the index I, we print A, B, C, and D. Once we have the new values of x1, x2, x3, and x4 in the variables A, B, C, and D respectively, we replace the old values of x1, x2, x3, and x4 by these new values. So x1 is replaced by A, x2 is replaced by B, x3 is replaced by C, and x4 is replaced by D. For the sake of example, we'll have the variable counter I go from 1 to 10. We execute all the lines of code. For comparison, the exact solution is given by this set of values. This is the exact solution up to 6 significant digits. We can take advantage of the matrix capability of Mathematica to avoid this rigmarole of having to store the new values of the variables in temporary variables. We rewrite the recursion in matrix form. To incorporate matrices into the code, we change the contents of the do loop. We call the coefficient matrix C1. We cannot use uppercase C for the matrix since uppercase C is a special symbol in Mathematica, so we use C1 instead. We type a pair of curly brackets for the matrix. Inside is the first row of C1, so we have a nested pair of curly brackets. The first row is 0, minus 0.4, 0.2, minus 0.2. The second row follows a comma after the first row and uses another nested pair of curly brackets. The second row is minus 0.25, 0, 0.25, minus 0.25. The third row is minus 0.25, minus 0.25, 0, minus 0.25. And the fourth row is minus 0.25, minus 0.25, 0.25, 0. We denote the constant matrix by uppercase B. Uppercase B is not a special symbol with Mathematica, so it's okay to use it as a variable. Like C1, B is a matrix, albeit a column matrix. Its first row is 1.8. The second row is 0. The third row is 2. And the fourth row is minus 0.5. Observe that, like for C1, we used nested curly brackets for each row of B. We now start the do loop. We start with the vector of unknowns. Its entries are x1, x2, x3, and x4. This vector equals C1 times the same column vector x1, x2, x3, x4. In Mathematica, we use the period for matrix multiplication. To this matrix product, we add uppercase B. We will print the iteration number I, x1, x2, x3, and x4. I goes from 1 to 10. We execute the code and get the same result as that of the previous incarnation of the code. Now for the Gauss Seidel method. We start with the same initial estimates for x1, x2, x3, and x4. Then we have the do loop for the recursion. The code is slightly more straightforward. From the first equation, x1 equals 1.8 minus 0.4 x2 plus 0.2 x3 minus 0.2 x4. From the second equation, x2 equals minus 0.25 x1. The new value of x1 will now be used not just for x2 but also in subsequent calculations. Then it's plus 0.25 x3 minus 0.25 x4. From the third equation, x3 equals 2 minus 0.25 x1 minus 0.25 x2. For x2 like x1, the new value of x2 will now be used here and in the formula for x4. Then it's minus 0.25 x4. And finally, from the fourth equation, x4 equals minus 0.5 minus 0.25 x1 minus 0.25 x2 plus 0.25 x3. We print the iteration number with the results of each iteration. We set I from 1 to 10. We execute the command to get the results from the different iterations.